Good afternoon. Am I audible to everybody?
Yes, sir.
Thank you. Thank you so much. Okay. So, welcome to the third lesson that we are covering on our journey on the business mathematics and statistics. So far, in the earlier two lectures, I explained you guys that we were just touching upon the basics. In the very first lesson, we want to discuss the couple of definitions and then what type of data that we are going to learn under this curriculum, and then what sort of primary versus secondary, and then again we got ourselves introducing to the words of the population and the sample. Then we learned secondary. Then we learned that uh, in in the real world, we are very much disturbed to get the access to the complete population at any point. So there only the wording of sampling came into the light. That's the second day that we spent on the complete discussion. What sort of sampling methods that are there in the popular statistical jargon? There are more. We discussed extensively eight into probabilistic and non-probabilistic. There again, you may have observed in the examination. The examiner is very keen to test your theoretical knowledge on the second subject area. The last week we entirely spent on ourselves understanding how to present those collected data. So that could be you may be presenting research, or you may be just answering an examination question. Whatsoever uh, you will be doing, you need to embrace some of the best practices. So the very fundamental tool that we learned on the last week lecture is nothing but the simple graphs and charts in order to present the data. But there, of course, students do not forget at any cost that whenever you are presenting yourself, and maybe you may be writing a thesis, you may be writing an assignment, you may be doing some important write up at work, or you may be writing this examination. At any point, just try to embrace the best practices of charting and graphing. Don't just jot down any graph without any axes names, without the zero mark, without the arrow signs. Just make sure you do a perfect presentation. So whenever there are some ambiguity, especially in the examination, there are some ambiguity towards when you're closer to the border line of the pass mark. Always your better representation that we learned under the second subject area will help you to gain some marks. So I would say previous two lessons, the three classes we spent on were mainly on qualitative aspects of the statistics. So from this point onwards, from lesson number 3 onwards, I explained this the same thing at the initial lecture also. This is the point we are touching the real statistics one by one. This area is completely on the central tendency and dispersion. So this lecture we have organized into two areas, part 1 and part 2. We are trying to cover this during two lectures, but failing in which there are plenty of ample important examination questions that have been tested on this subject area, lesson number 3. So I want to spend maximum time with you guys to make yourself very familiar with the pattern and the style of the examiner's questions. So failing in which we can't finish this in the upcoming class, we may spend some time on the third class also and try to finish this area before we move on to probability, that is the fourth subject area. So before we step onto this area, let me just give you a glimpse of what sort of questions that we can observe in the examination paper. We discuss again and again. There are two aspects of our discussion. One is to give you this superior knowledge on the statistics, the introductory parts on the mathematics and business statistics. And the second part is your examination. That's the core, and that's the quality time that we're spending on this Sunday evening to pass your examination. So on the examination aspect, what you could say is that categorically, if you look at 2019 September, 2019 March kind of nearby examinations, you will see plenty of 2-mark questions, or maybe something like a 5-mark or a 10-mark allocation in the elective parts being tested in the areas that we are going to discuss under central tendency and dispersion. And also on the second area on the dispersion that we are going to discuss today, central tendency is all about use of learning on mean, median, and mode, and trying to identify these identifiers of a data set and try to calculate it or find it. That's it. On the dispersion, the second word that is on our topic, that gives you a stepping stone into some advanced statistical equations. So the word dispersion is going to tell you a particular selected data, how deviated or how long it is from a central tendency point that we are going to define. Categorically, mean will be a very good example, and you will understand it why. And importantly, at the lecture one also we discussed that in the previous examinations, you will not be given the equations in the last page of your examination paper. So there are some equations that we have to keep practice and remember. It's not much. It's not like a 50 or a 70, maybe 15 to 20 kind of a set of equations. You can nicely jot it down in a A4 sheet at the end of the lecture sessions, and keep practicing it a couple of times, and you don't have to really by heart it. As long as you can get the glimpse of the equation, that is pretty much sufficient. So what I want to stress here is that in this lecture, there are some equations that you will be given with a red square highlighted area, which you will be needing at the examination. Sometimes you may see that it's not necessary to remember the exact equation, but there are some nearby examinations in 2018 and 2019 that shows you the subject area on dispersion, and after the probability we'll be discussing the multivariate analysis. Certain equations that is coming from the dispersion and those areas, examiner is in the expectation that you will be in a position to apply them as it is. So it's important to spend time from this point onwards to keep a couple of short notes also on the important equation, so that you won't need to really by heart it near the examination. Because once again, I implore that this is an optional subject. You have plenty of compulsory subjects to focus on. There are a lot of theoretical areas to be studied. So just keep practice these questions and the equations in a corner of your mind, so that you will be in a very comfortable position near the examination. Okay. Having said that introduction, let's move on to the today's lecture on the central tendency and dispersion. Okay. So as I explained you, we have two parts of these lecture slides. There are 66 slides. The first couple of parts is on the lesson of central tendency and dispersion. If I quickly take you to the last couple of this slide and show you where we are going to break for the second session. This is we are expecting to cover in the next week. That is the part 2, where we'll be discussing some of the theories on the normal distribution of a particular data set, how it is being constructed, and what sort of qualitative aspects like the skewness, the curvaceous, and the other areas that we can discuss. And on this third one, covariability, you will be introduced to two variables in a particular data set. Okay, so this is going to be the next week discussion from slide 40 onwards, and hopefully we are going to cover contents that I'm going to show you today. Okay. We'll take an introduction to what the descriptive statistics is all about. I mean, the qualitative aspects and the numerative aspect of the statistics, and give you an introduction to what the central tendency is. And under area 3, we will be discussing mode, median, and mean. That are the main 3 measures of central tendency. And area 4 and 5 is on the dispersion. That is the starting point of those equations that we discussed a moment ago. And we have plenty of examination questions to practice today, a lot of MCQ questions. So while we are doing the questions, I suggest that we can use the chat feature on the Google Classroom today, and just shoot on the answers, and we'll see whether we all are getting it right. This is the learning point once again. Don't be nervous to put up your answer. So just that as long as you you practice these questions again and again. Even if you're wrong at a particular question, still you will be in a comfortable position. Okay, right. That's the introduction for the day. We'll start with the first subject area on the central tendency and dispersion. So, the descriptive statistics, the word, is involved in data collection, organizing, and presenting an analysis. So that's the first two lessons that we learned so far. We learn to, the class example of this 70 students case, mathematics marks. We learn to collect data, organize them, and present them for analytical purposes. So that's the basis of any statistic. So it can be used to explain a sample data set by means of graphically or numerically in the concise manner. So the moment we want to use a particular sample to represent the entire population. Remember in our earlier example, 70 students, we were not interested to talking to everybody, but rather select maybe 20 students. Or I could say there are 700 students and I could talk to 20 students to get some understanding on the mathematical model. So the descriptive statistics is all about you are trying to uh, sort of try to get an understanding of a complete population by studying a sample set of data. The third point I want to stress is the complete data set using a sample is called the inferential statistics. So the moment you have the access to the complete data set, the reciprocal word of descriptive statistics, the inferential statistics is coming into the picture. So far, what we have discussed under lesson 1 and 2 are very easy examples of maybe 70 students or maybe 10 coconuts or maybe 20 kilograms of rice. So likewise, where you don't really get involved in hundreds of thousands of many more data. So the inferential statistics is the introduction that we are going to take from this point onwards. That is where we don't necessarily go and discuss about individual data, but rather we will be discussing about a population or a sample by using some of the properties and the characteristics of the data set. It could be the entire population or it could be a small sample that we have gathered. So, okay. So this is the deviation. The first 2 points is about the studies that we have taken so far, and the third point, the inferential statistics, is the point that I'm going to take it from next point onwards to talk about some characteristics of a particular data set. So the moment when you really want to express about a particular data set, you may not in a position to get a perfect representative. Let's say, for instance, in our 70 students example, let's say we want to take a particular student and ask that student, okay, now you are going to be the representative of this particular 70 student batch. But can that student be a perfect representative? It might not be. So you may think, okay, why don't we ask the class monitor? If it's a school, we can ask the class monitor to come and be the representative of the class and go and present itself. But okay, that's fine. But then again, there may be various other ways to represent a particular data set. Then again, the most important point is there is no one perfect representer for a data set. If it is a class, if it is a pile of coconuts or anything, there is no one particular element to be shown and say that, okay, now this is the perfect representer of this complete data set or the complete basket of goods or items. So the central tendency, the word central tendency is coming into the picture in light of such circumstances. So we are in need of finding some representatives for this data set. There, of course, depending on the nature of the data set, there could be many types of representatives. In our class example, we One could say, okay, we'll take monitor. One could say, okay, we'll take the vice monitor. One could say, we'll take the chap who becomes a first in the class. One would say, we'll take the first person. Let's say Abhay Sekar, maybe the surname of the first person, and we'll take him since he's in the first in the register. Likewise, there could be many different ways to pick that student in that exam. Likewise, in the central tendency jargon, there are many identifiers for a particular data set. It could, once again, I stress this point again and again, it could be the entire population or it could be the selected sample data set. Okay. The idea of a central tendency indicator is to describe the data set. It should be the representer, or the moment when you look at that particular data point, you should be able to get an understanding. Okay, if we have, let's say, 20 baskets of coconuts in a basket, 20 coconuts. The moment you pick a particular coconut, the weight, the size, you should be getting an understanding, okay, now the other items in that particular 20 basket of coconuts should be similar to this particular coconut that I'm going to show you as a representative. Okay. If you could recall some, classic examples like in Peta market, when you go to these wholesale stores, there are, some huge piles of wheat and flour and many more items. But when you really want to go and test something, you can't really go and check out all the bags of rice or all the bags of dal. Rather, there are some samples to be shown. So you expect, when you look at that particular sample, you expect, okay, now this should be the quality of the other elements in those bags. Similarly, this central tendency, we are going to learn three particular measures that is going to represent the data set. It could be 10 numbers, it could be 100 students, or it could be millions of population. The names of these representers are nothing but mode, median, and mean. Now, once again, if you recall that these may be the simple identifier that you have learned in your early studies of maybe grade 10, 11 mathematics, but that's okay. We'll refresh our knowledge on these three items, mode, median, and mean, but categorically, under business mathematics and statistics, the important point that you need to stress upon is to identify the limitations, the usages, and to take real world effective decisions whether those identified are suitable or not. That's the complete decision that you have to make. Say, for instance, now we will be learning what are the similarities and some of the limitations in the mode, median, and mean. The whole idea is that once you be given a particular data set, you should be in a position to identify whether, okay, am I looking at a qualitative data set? Am I looking at a continuous number series? Am I looking at some discrete couple of numbers? Am I looking at some data set with some class intervals, some frequencies? So depending on the nature of the data set that you have been presented, you need to carefully pick one of these central tendency indicators and represent the data set. Meanwhile, you should understand whether you are going to use one or two or maybe all or maybe just one and omit couple of the other indicators and saying that these will be not necessarily used in these instances. So that's the whole idea of the next couple of slides. Not to, examiner will never give you maybe 50 numbers and ask you to pick the mode. That's not the type of learning that we are expecting. Okay. So we'll take a moment and try to understand what these three indicators are. The first indicator is nothing but the mode. It's the most frequent occurring item in a particular data set. Okay. So one classic, let me just try to use the board here. Let's say you have a data set of 7, 9, 9, 9, 10, 11. Okay. Now in this instance, this is 7. This is the mode. Why? Because of the fact that 9 is occurred most number of time in this data set. Okay. What if you have What if you have the data set like this? You have 7 here, 3 nines here, 3 tens here, and 1 11. It's an instance of multiple modes. So you have number 9 and number 10 as modes. So a particular given data set could have maybe one mode, or it could have multiple modes depending on whether you have one most occurred number or the same frequency with couple of numbers. Like in this example, you have 3 number of nines and 3 number of tens in the data set. Okay. That's the second point I have stressed here. You may find single mode, dual mode, multiple mode, or no mode instances of a particular data set. So in that example, let's say you have the numbers like 7, 8, 9, 10, 11, so on and so forth. So the frequency of all these values are nothing but 1. So in this instance, you can say there is no mode in the data set. Or you have to nominate every data point as the mode. So single, dual, multiple, and no mode instances could be there in a simple number set. Okay. So can we define modes for qualitative items also? We can. Okay. Let's say assuming that nature, size, everything is similar. Let's say you have bananas, coconuts, and mangoes, and few other vegetables and fruits. So similarly, you put everything into one particular place, count them, and still you can find a mode for a particular item. These are some of the characteristics of the mode. Third bullet. Mode is not affected by extreme values. Now these are very important statement. What are those extreme values? I'll come to that in a while. Give me a second. Second point we'll take. Mode can be calculated for a data set with open class intervals. So last week, if you could recall, we discussed some group data. Sometimes you can take individual items, or rather you can group them, maybe 10 to 15, 15 to 20, likewise. So the other indicators that we are going to discuss, sometimes categorically mean, could be sometimes be disturbing when you're going to calculate for open class intervals. So what you mean by an open class interval is an class with a maybe towards the 0 or maybe towards the infinity. It doesn't matter. So in our case, as long as you have maybe a couple of classes, maybe let's say the third class or the second class or the fourth class will have the maximum frequency compared to these other intervals. Still, you can omit these open class intervals and say, okay, class number 4 is the mode class. So that's the instance where you have a group data. Point number 2. Point number 3. It is a measure which can be also derived by using graphs. Pretty easy. You plot them in a maybe bar chart, and visually you can quickly identify what the mode is going to be. Last point. A good measure to explain average values of a data set in a qualitative manner. So, I mean, that would be rather a qualitative statement. But then again, it's a very easy measure to calculate. Nothing, I mean, no calculations involved. Just you have to count the number of instances. So it's a good measure to explain average values of a data set in a qualitative manner. But the word qualitative manner gives you an indication that this value is not being derived by a quantitative method, like we are going to discuss in a while about mean. When you calculate MEAN mean, you will be using some quantitative methods to calculate it. Okay. So it's an easy measure to explain. Now in our early example, 7, 9s and 10s, you could say, okay, most number of frequent occurring item is 9. So let's say there are a number of telephone calls coming for a particular garage on inquiries. There may be one call, two call, then there may be 9 calls, maybe a couple of times, and then at one day there will be maybe 20 calls. So in that instance, you are going to estimate roughly what's the number of calls that you are going to get. One could say, okay, around 9 to 10 easily. So that's the mode's real application. Just looking at a data set, look at the most number of occurring data point and identify that as the representative. We'll come to the first point. What do you mean by this? Extreme values. Okay. And quickly go back to the board once again. Now, students, now this example we discussed a moment ago, we had 7, 9, 9, 9, 10 and 11. Okay. So instead of 11, I'm going to change this value to 11, 11, 1111. Okay. This is a one particular number. If you look at these numbers, you could say 7, 9, 9, 10. I mean, these all these numbers are towards 0, while this number is a 1000 number. But still, if you are being given to represent this number set by using one central tendency indicator, you will still select 9 as the mode. So, but if you look at this number set, you could see some weird indication that this 1111 seems to be an extreme value. It's an outlier. If you plot these numbers, there will be some numbers here, and then there will be one extreme value towards the extreme side. So even though in a data set like this, even though there's an extreme value, still if you are looking at mode will not be getting disturbed by extreme values. So once again, let me reiterate, it's a qualitative statement. Say imagine now in this the same example that we discussed a moment ago, 999, and then there may be 3,111. Still, it is going to be getting disturbed, or rather, you will identify this mode as pretty non-user friendly at such instances. But then again, given one or two extreme values or an outlier, still the mode will not be affected. Now, these kind of statements, when we move to the second part of the day on the examination questions, you will see plenty of these kind of statements being tested again and again by the examiner. Okay, so that's about mode. Reiterating, it's the most frequent value for a given data set. Pretty much useful, easy to. It's a good measure to explain an indicator in a qualitative manner, no quantitative computations. So it's useful in many ways, and still it's just one number in a particular data set. And maybe instances like where you have no modes, still this is not going to be a good representative or a good identifier of central tendency. Okay. So having a little understanding on mode, let's move to the second one, median. This is also very easy. It's nothing but the middle value, but provided we arrange the data set in an order. Could be either way, it could be ascending manner or descending manner, but in the definition, we call it an ascending manner. It's a value which will come to the middle point when we arrange the given data set or a frequency distribution in an ascending manner. You'll understand what these frequency distributions at the second part, don't worry. But when you look at a data set, let's say we are going to discuss an easy data set, okay? 1, 2, 3, 4, and 5. Try to visualize them. 1, 2, 3, 4, and 5. That's our data set. It's in the ascending order now. Okay. So in this instance, number 3 is the middle point. You have 1, 2, and number 3, the middle point, then 4 and 5. We are happy. One median value. But what if we introduce number 6 into our picture? Now there's no one middle point, isn't that so? So you have 1, 2, 3 in one side, 4, 5, 6 on the other side. In that instance, what we do in the median is that it's not a number, it's not an actual number in the data set. Rather, we take 3 and 4, add them up, divide them by 2, and define 3.5 as the median in the data set. Okay, that's the instance for the odd and even numbers when we are doing a uh, arrangement and try to identify the median. Now, one would say, okay, it's not a pretty advanced statistical computation, isn't that so? So what's the big deal on the median? I mean, uh, once again, it's like mode. It's just one number. There's no numerical computation involved here. But then again, when we go to these frequency distributions, the normal distributions in our second part of the discussion, you will understand that it's pretty important to identify the middle point or the 50% mark also. There are many usages in that. So you could say up to this value, a 50% data set is being represented. And from this point onwards, the next 50% is going to be represented. Likewise, this 50% identifier is pretty much useful in when we are discussing large number of data. With thousands and millions of data, it's pretty important to identify the 25%, 50%, 75%, sometimes the 97.5, 99.6. These are some statistical numbers that is having some significance in defining things, taking decision. That's why we learn about median here. Look at the second bullet point. Let's look at some of the characteristics of the median. Okay. It's a unique measure which can be demarcated always. So it could be a number in the data set. It could be not a number, but then again a derived number. However, it's a unique number. Okay. So unlike the mode where you could see 2 or 3 modes, can there be multiple medians? There won't be. It's a unique number. It's one single number. Okay. No influence from skewed outlier value. Similar to our example, that 1111. Now that's an outlier. In that data set of 7s, 9s, and 10s, that's an outlier. That 1111. But even if that number is there, it's just a number, one position in that particular data array. Median will be still a number in the 7s, 10s, and 9s. Okay. So, irrespective of the fact that there are outlier values, still median could be nicely computed. And it won't get impacted also. It won't get influenced. Look at the third point. Ability of computing when all the observations of data set are not known in distributions with open class intervals. So similar point that we discussed under mode also. Going back to our last week discussion, when we define class intervals, let's say we have 10 to 15, 15 to 20, 20 to 30, and 30 to 40. Now from 40 onwards, we're not discussing. From 10 below also, we're not discussing. So we can discuss some open class intervals from 0 to 10 and from 40 onwards. But in those instances also, when there are open class intervals, we don't know whether there will be any more values that can be come into those last classes. But still, those are just one class, isn't that so? From 40 onwards, it's just one class. From 10 below, just one class. You separate them and just focus on the middle classes. Maybe your fourth or fifth class will have the median class. Easy as that. Last point, being a good measure of central tendency for extremely skewed distributions. Now, what does this say? This skewness, I showed you at the beginning of the class also. Skewness is another central tendency that we are going to discuss in the second part. Rather, I call it a central tendency. A much more appropriate value will be, it's a nature of a particular data set. It's a nature of the distribution of a particular data set. So, the skewness, the word skewness means whether we are looking at a balanced distribution or an unbalanced distribution. So, the moment when we have an unbalanced distributions, the middle point is very important to define certain statistical indicators. Some of them which we will not be discussing under this curriculum, but the middle point definition is very important, not at the very balanced data set, but rather at the extremely skewed or extremely, you know, deviated distributions. You have couple of ones, twos, and threes, and then many thousands, 2000s, 3000s likewise. So it's very skewed. So in those instances, the median or the middle point shows you where we will be demarcating the 50%, first 50% and the second 50%. Okay. So the most important characteristics that we are going to take away is that uh, there will be no influence from the outlier values, and it's a unique measure. It's a one unique measure. And can it be a number always in a time series? It could be, or sometimes for cases where you have no one central point, you will have to take two adjoining numbers and divide them by 2 and define a number. So it could be a unique number which is in the data set, or maybe you have to derive that number. However, it's a unique number and will not getting influenced by outlier data. So far, two simple indicators we have learned, mode and median. But this is the real numerical indicator of a particular data set, and I would nominate this as the most suitable indicator for a particular data set and most widely used indicator for many statistical data that we are going to discuss uh, in any jargon. That is the mean or the average. Once again, this is the arithmetical mean or arithmetic average that we are going to discuss here. There are many means like geometric means. It could be coming from various series of data. But then again, the whole idea of our introductory statistical session is to understand the basic mean, that is the arithmetic mean, and the applications of it from this point on. Okay. So mean is nothing but the average of a particular data set. You add the values of all numerical numbers of a given data set, given set of numbers, let's say, divide by the number of items, and you will have the average number. But before we move to the numbers, what about the qualitative data? Now, let's say we had previously we had some mangoes and papayas and then some bananas. In those instances, can we calculate a mean? It cannot be. So that's why we discussed at the beginning, for certain data sets, for certain items, certain baskets, bags of data, where categorically qualitative data is available, it's very difficult to take mean or median, but rather mode will be a good representative in such instances. So the moment we are going to discuss mean, always keep in mind that we're talking about numerical numbers, because there's going to be always a division by number of items and then discussing the average. Okay. We'll see what the definition on the second bullet point. When each observation of a population contains capital N, it's an important thing to understand. The moment I am going to use the word population, I'm going to use the word capital N. And the moment I'm going to talk about a sample or a small part of the population, the sample, I'm going to use the word simple N. So whenever in the equations you see a capital N, simple N, always remember what we are referring to. Capital N is for the population and simple N is for the sample. Back to the second bullet point. When each observation of a population contains capital N number of data donated by x1, x2, x3 and up to x capital N, the mean of the population can be derived by this equation. So I want to again spend a couple of minutes, since this is the first time you will be introduced to this sign. What is that sign? We call that sign as a sigma. This is the sign. Sigma. Sigma in statistics is the word for addition. You have a couple of numbers, x1, x2, x3, and let's say these will have some values. Let's say x1 is 10, x2 is 20, x3 is 30. Now, if you have a sigma, the operation that you have to do is simple. You have to add these numbers together. Simple as that. So the sigma of these numbers, if I ask you, you have to tell me it is 60. 10 plus 20 plus 30 is going to be 60. Okay. It's a starting point of getting known to sigma. So that's why I have used this identifier. And when you carefully look at the definition, the population mean, and then you have the sigma mark, then you have some more numbers. Simple I is equal to 1, and then there's capital N on the top. What are those? Again, when, sorry, at the definition of, right, at the definition of sigma, over here, we are going to write, okay, what is the starting point of this number of additions? When I say simple I is equal to 1, it's going to give an indication, okay, my addition, number of points that I'm going to add for this sigma, I'm going to start from the first item. If I say I equals 2 to n, it is going to give you an indication, okay, I have to omit the first number. First number I'm not going to take for the sigma, but from second number onwards I am going to add. Up until which number? That is the number that I'm going to write here. When I write capital N here, that means this is the end point. End, END, end point. Okay. So you have the first point here, the second point here, third point here. Similarly, let's say you have the capital Nth number here. This is the first number, this is the second number, this is the third number. Likewise, okay. First point, first position. So you may have 10 here, you may have 35 here, you may have 40 here, and you may have a 65 here. Let's assume that this is a ascending order number series. When I say I equals 1 to n, this is going to tell you to add all these numbers from 1, 2, 3 up until this n position. Instead of 1, if I write, let's say 3 to n, this operation is going to define you, okay, I have to add from number third point, third up until capital N. Can I use sigma for a deduction? No, sigma is always for addition. Can I define something funny like this? Let's say I'm going to define from I equal 1 to 3 here. Yeah, you can. It doesn't necessarily have to be, up until the last point. So this operation is going to tell you, okay, I'm going to sigma, I'm going to add the values first to third, first, second, and third. So the summation will give you a value of 85, adding these three numbers. Okay. So the definition of our simple average calculation is going to be like this. You add the values, use the calculator, add every number and divide by the number of items. It is going to give you the mean or the average. This is how we define in mathematical and statistical language. You have population mean as I equal 1 to capital N xi. Xi means the number that you are going to write in this particular data set. I have written I equals 1, 2, 3, likewise for this particular array of data. I'm going to add everything, divide by capital N. Bang, we have the population mean. So let's say our population has 700 students. This X is equal to the weights. Our class example, not the mathematics marks anymore. I'm going to nominate the X as the weight in kilograms. Let's say you have 60 kilograms up until 70, 80, likewise. Simple as that. You get everybody, measure their weight by using a scale. This xi will be the first student, second student, likewise up until the capital N will be the 700 student. You get these numbers, divide by 700 as the capital N, which is going to give you the population mean. But instead of the 700 students, if you take 20, now instead of 700 in this capital N, this simple N is going to be 20. Sample, the smaller one, smaller portion is going to give you the sample mean. Important to understand. Uh, so sometimes you may have the luxury to, like in the 700 students weight measuring exercise, you may have the luxury to do it. But talk about 22.6 million population and derive their daily income or derive their daily expenditure pattern or derive their, let's say, some expectation on the economic growth, some weird number like that. Those are pretty much away from you. So population is not always accessible. Always remember, that's why we again and again discuss about a sample in our discussion in statistics. Okay, done. We get to know the basic definitions of mode, median, and mean. These are some characteristics of the mean. First point, it represents total observations of a data set. So, what are the other two indicators like mode and median? Doesn't they represent the entire data set? It does not. It does not. Why? Mode we learn is just most frequently occurring value. Median, the middle point. But what about mean? How do we calculate mean? We took everything, the numerical value of every item in our data set. We used every item and then we derived the mean. Because of that, the first point says it stress. It represents the total observations of a data set. We had to use the numerical values of all numbers to calculate the mean. Second point, ability of using as an algebraic function. What do you mean by an algebraic function? Y equals mx plus c, y equals a plus bx, y equals ax square plus bx plus c kind of algebraic equations. You can jolly well put mean as an algebraic identifier. We call it x bar. Mean, although we define population mean and sample mean in the slides, the value that we are going to get calculated here will be denoted as x bar, y bar, t bar, p bar, or any bar. What you mean by a bar is something like what I have shown here. If you carefully look at this mean equation given in the third point, you could see that I have put a small bar on top of this small x1. Bar is nothing but the average or the mean. Okay. So now we'll come to the third equation in a while. But what do you mean by the second point? So can't we take more than median as an algebraic function? We can, but that doesn't give you a sort of a meaningful equation in algebraic form. Can we plot an x value for y equals mx plus c, and for that smaller x number, what if we put mode? It will not give you a representative, or rather it will give you one particular value which will be extremely biased towards the mode or the median that we calculated for the data set. But instead, if you use mean, mean is a carefully crafted identifier or a representative. So at any instance, when you use a particular value for a representer, that has to have the characteristics to express all the values in the data set. So that's why we use mean fearlessly in algebraic functions at any instances. The third point is a good example to elaborate the second point further. Once the means of few data sets k number of data sets. That means 700 students, 800 students, 1000 students separately. 700 maybe from one school, 1000 maybe from another school, likewise. Several data sets, k number of data sets, okay, are known separately. A single mean can be defined by combining them as follows. The equation I've shown here, it's not an equation to be applied at the examination, but I'm just trying to express it with some meaningful numbers. We discussed 700 students, 1000 students, 1200 students, 500 students. Likewise, we have now couple of separate data sets from, let's say, separate districts, and we know the means. Okay, so we don't necessarily have to add everything together, add individual numbers of those 700s and thousands and 1200s, and put everything and divide by maybe 3500 to get the mean. Rather, you have the mean, multiply them by the number of items, add it. You have the mean multiplied by the number of items. Now, when you multiply these two numbers, simple n1 and simple x1 bar, what is the value that you're going to get is the total weight of the numbers. Now, when you have 1, 2, 3, 4, and 5, you will add them together and calculate a particular mean. Okay? You will get 3 as an answer. So, when you multiply 3 by 5, you will get 15. 3 into 5 is 15, isn't that so? When you add 1, 2, 3, 4, and 5 also, you will get 15. So, the moment you multiply the mean by the number of items, that is going to give you the total weight of the basket that you're going to discuss. So, similarly, the third bullet point, what you're going to show here is that once you know the particular mean of one simple data set, multiply that by number of items in those particular baskets, then divide by the individual numbers. This is 700, this is 1000, this is 1200, likewise this k number of items. Easily you can calculate the complete mean or the composite mean. I mean, for a class example, that sounds like maybe just 4 or 5 number of samples. So why don't you take all the data points again and divide by 3500 and get the mean? Fine, yes, of course. This equation doesn't make sense for a small number of k, but what if the k is extremely large? Let's say you're talking about thousands of data sets. So that is why just I want to express this equation here. When you have multiple data sets given with multiple means and number of items, you can use an equation like this and calculate the composite mean. Okay? Not a big deal. Being an identical measure again, it's a unique measure similar to the median we discussed. It's a unique measure. A relatively reliable measure, last bullet point, which does not deviate much from a sample to another sample. What do you mean by this? Now, when we have the 700 students class, let's say it's a very large group class, if you take 10 samples, you randomly take 50 students at a time and carve out maybe 10 different samples, and then when you use those samples and calculate mean, median, and mode, okay, I repeat, you have 700 students. At 10 different instances, I randomly choose 50 students to be my sample. And let's say I'm going to measure their weight. It's an easy thing to do. Put them in a small scale and measure the weight. And I'm going to do a study. In that instance, what I want to highlight here is that if I calculate mode, median, and mean, for mean, you will have a lesser varying value. But for mode and median, depending on the randomness of the data, you will have some extreme numbers. So the first 50 students, let's say you have some extremely skinny students, though they may be having 35 or 40 kind of weights. So if you calculate the mode for the first data set, you will say 37 as the mode weight of a particular 50 student class. But If you take all these numbers and divide them by 50, your mean will be somewhat maybe 41, 42, closer to those students. True representation. And when you do that for the 10 samples, for the mean, you will not see a much deviating value compared to another sample. That's the last point I want to stress here. So because of that, why does it happen? It's because of the randomness of the data. So let's say randomly, I've selected some most biased weighting students for a particular class. So that class will have some disturbing numbers for the mode and median. But still, if you calculate mean, it will give you a much more reliable number. And when you do the comparison between maybe 10 different classes, for mean, you will always get a much more reliable measure, which will have no major deviation. So for the first class, if you take the mode, you will have 37. For the second class, for the mode, you will have, let's say, 41 or something. Third class, you will have 73 or something. Why? Because maybe those 50 students, you will have only two students with a similar weight, and those students are extremely fatigued, maybe 72 or something. Okay. So for the mode, you will have much more deviating and varying values, but for mean, you will not have it statistically. Okay. So a lot of qualitative things to keep in mind, and I have two more such qualitative measures before we move to the next areas on the numbers. So bear with me and try to understand these, because if you look at the examination questions in the latter part, last half an hour, you will see plenty of these being tested again and again. So these are some relative advantages and disadvantages of mode, median, and mean. Now this is the level of expected proficiency that we are expecting from you students at this point. Not to give some 10 numbers and ask to calculate mode, median, and mean. Okay. Let's look at them one by one. Mean is a good measure since it considers all observations of data set compared to mode and median. That I hope you understand now. Compared to mode and median, true that we look at all the data points and we select the mode and median, but still mean is a computed value or a derived value, a calculated value using all the observations. Second point, mean and median are identical measures compared to the mode. Mode is a most frequently occurring number. It could be multiple numbers, multiple modes or no modes, such instances. But median and mean are identical, uniquely calculatable measures. That's the second point we need to keep in mind. Third point, given qualitative data, what are the qualitative data? Like mangoes, colors, countries, likewise. Mean is meaningless. Mean is a meaningless measure. You take 187 countries and ask what is the mean of these countries, there is no particular answer. So a basket of qualitative items, you ask what is the mean is not a qualitative, mean is not a meaningful representative at such instances. While mode and median sometimes are still usable, not always, sometimes are usable in some instances. Fourth point, when there are open class frequency distributions, mean cannot be computed while mode and median are useful. We'll see why mean cannot be computed when we are touching upon those lessons. For the moment, just keep in mind. And under mode and median, we discussed this point a couple of times, that when there are open intervals, we don't have to worry about those end classes. Rather, we can focus on the middle point or the most frequently occurring point and calculate mode and median. But for mean, we cannot do it. For mean, we need to identify each and every value. So if it is if a class is open and if you don't know what value are going to be in that class, you cannot calculate the average. It's not possible. Fifth point, mean is highly influenced by extremely skewed values, while mode, median are not. I'll quickly come back to our small data set once again. You could recall our small data set of 7, 9, 9, 9, 10, and 1111. Mode, fine. Median, fine. 9. What about mean? When you do the math, when you use sigma, I'll show you what the mean is going to be. You have to add 7, 999, and a 10, and 1111. I hope you have a calculator in your position. I get the sigma as 1155. I have 6 numbers here. I divide it by 6 and I get a mean x bar as 192.5. This is the mean of this particular data set. But if you look at the data set, what do you see, students? You have 7, 9, 10. These are much more towards the 0 and 10. So this is a classic data set of let's say some Likert scale. It could be anything. But what about this number? This outlier has caused the mean to be an extremely large number. So this mean is now in between somewhere here. Isn't that so? Somewhere here. Not at this end, not at this end, but somewhere here, but again close to 1111, closer to that extreme end. So that is a point I have highlighted there. Whenever there are extreme values, your mean is going to be getting impacted. It's a very important point and a very trivial weakness of the mean. Mean is highly influenced by extreme and skewed. Skewed are again biased or deviated values, while mode and median are not. That's the main weakness of a mean. So in some of the practical applications of statistics, what do we do in such instances? Let's say you're talking about a particular company's profits in a quarterly wise. Okay, looking at a manufacturing company, you have profit numbers. Okay, the profits could be deriving from normal operations, and it could be deriving from various other one-off activities also. Let's say you sell one particular big asset. That year you may have a thumping profit to be realized. So you look at particular set of numbers. Okay, it's like a pulse, like a heartbeat. You have some ups and downs, but all of a sudden you see a jump. So that's the outlier number. Now you know this weakness. You know that whenever there is an outlier, your average, the mean, is going to be impacted. Simply you take that value out. That's the practical application. So when you have an outlier, that's one of the easiest things to do. There are many, theoretical statistical ways to do it. I mean, there's no one particular outlier in a data set. When you look at millions of data points, like in big data analysis, there's no such easy example where you see one particular instance where you can chop it off and say, fine, that's an outlier, I'm going to call it off. Okay. But in reality, now in this 1111 is an easy number. You could say all the other numbers are in the 10 to 0 range, while this number is extremely deviated. But what if I put 22 here? Could you say it's an outlier instead of 1111? It's a bit tricky, isn't that so? One could say, yeah, 22 seems to be a closer value to other numbers. But 1111, obviously, it's an outlier. In that ground, this obviousness, that qualitative statement is a bit tricky when you have millions of data. Okay, that's on the point number 5. Sixth point. Mean can be used as an algebraic function, but mode and median cannot be used. Of course, we discuss it under the mean section. Last one. Mode and median can be defined graphically, but mean cannot be derived as such. What do you mean by that? When you put all these numbers in a small graph or a chart or a frequency distribution, mode and median can be graphically easily derived. But can you define mean like that in graphically? You cannot. You have to add the values, divide them by the number of items, and then only you can derive. But looking at the qualitative aspect, looking at a graphical aspect, you cannot define mean, right? Great. Last uh, bit of qualitative discussion before we move to the second part of the day on the dispersion. This is where uh, mean, median, mode are usable or good measures in practical applications. We'll quickly go through. Mean. When data of qualitative variables are given, such as mass, length of objects, exam marks, sales revenue, things like that. This word should be quantitative. I'm sorry about this. When data of quantitative variables are given, such as these examples, the mean is always good when there are quantifiable numbers. Okay? I'll correct this in the slides also. Second point, in the absence of skewed and extreme values in the dataset, like we discussed, whenever there are extreme numbers, you cannot use mean as a good representative. Median. When data of qualitative variables are given, those are fine, yes. Like consumer desires, attitudes. I mean, those cannot be necessarily numbers, but rather you can just order them in a particular manner and then identify the middle point. What do you mean by an example like consumer desires? Let's say, how do you measure it? You could say whether you like this particular product. Could you, indicate your likeness by using a Likert scale, using 1, 2, 3, 4, and 5. 1 is extremely dislike, 5 is extremely like, and 3 is somewhat indifferent. Likewise, these qualitative measures, you can get some sort of a quantitative identifier. So for that matter, you can still use the median. Second point, when measure free from skewed and extreme values is needed as an average. In our same example, now when you have a extreme value and when you still need a representer, median could be a good number to represent. Third, when a measure is required to show the average of a frequency distribution with open class intervals. It's open class discussion, the same point that we discuss again and again. Lastly, mode. It is useful when decision should be made in abundance or no access to all data, such as when determining a set of shoe size. What do you mean by this shoe size example? You need to, you're going to start a shoe company in Sri Lanka. Let's say Gen shoes, office shoes. You don't have access to all the population who goes to work, who wears this official shoes, not casual shoes, but official shoes. Then you have to, always go to a sample and then see what's the most frequently occurring shoe size, maybe UK 7, UK 9, any standard size, and then produce your maximum output towards that, because that's the most frequently visiting customers. That's of course it is going to be. So still you have to make a decision. You don't have the access to all the data. Still you will have to make a call and make a particular bands of shoes in a particular defined sizes. You have to use the mode as the best. Can you use mean in this example? Can you add everybody's shoe size and take average and produce everything to that mean? It's going to be an absurd decision making. It's not going to be work. Right? Last one. When data are highly concentrated around a particular value. When you see a qualitative aspect like this telephone call example we discussed. Let's say it is a bank and number of telephone calls, or bank and number of complaints. You need to get the number to make a particular decision. Mode is an easy number, quick calculatable number to make that decision. That's about it. It took a little more time than I expected, but I hope it was a fruitful discussion on the first part of our discussion on the central tendency. Okay. Right. This is the second part of the today's discussion on the dispersion. Okay. Dispersion, the word, is going to give an understanding on how varied or how far away a random selected number from a given from a particular data set from the defined average. Okay. Usually, the moment you're going to discuss about the dispersion, you're going to discuss the mean or the average of a particular data set. So far, we have identified, okay, fine. We are on statistics, on quantitative numbers. Okay. Under such instances, we will be discussing about an average or the mean of a sample or a population to be our representative. If continuing our last discussion on area number 3 on the central tendency, out of all three, if I'm being asked to select one good representer out of mode, median, and mean, I will always select mean as the representer. Okay. Under such instance, the dispersion word comes into play to show you a particular randomly selected number. These indicators that I have put it in the fourth point, range, deviation, variance, and standard deviation. These are going to tell you for a particular randomly selected number how far on average it is going to be from the central point that we are going to select. How far that particular point is going to be from the central point that we will be discussing. That's the word or the simple idea of dispersion. In complete sense, we can define as the scattering of data of a given data set. The extent of the observation being apart from average value of a data set is explained by the word dispersion. Why do we need to understand it? Simply because of the fact that the next number or the randomly selected number in our data set, we don't necessarily know how bad it is going to be or how close it is going to be. So we still need some more identified. We can't be really satisfied with mean, median, and mode and say, okay, we are done. We still need some more indicators to understand a particular data set, whether it is scattered towards one central point, whether it's towards zero, whether it's towards the midpoint, towards an extreme end, or whether it's nicely and evenly distributed. That's the idea on this area on the dispersion. Third point, some uses of dispersion are its ability to understand how data is scattered, what we discussed. We need to get an understanding of a randomly selected number. If you have a dispersion indicator with a high number, a very large number for these indicators we are going to calculate, you could still say, fine, it's a the next number is not going to be a really reliable number. I'll take a pause here and I'll show you a classic example. We'll think a lot of us we like cricket in this country. Let's say we're looking at a particular batsman's average scores. Okay, he may have scored 12, 37. I'm talking about a one-day international. Okay, normal cricket matches. He may have scored maybe 12, 37, 50, 100, and then 102, then a couple of zeros, then some 50s and 60s, and eventually you will see an average of maybe 37 or 40. Okay. Now he has only scored maybe 30 or 40 matches. Fine. Now that average, students, is coming from how do you calculate the average? You add everything, even those zeros you have to add it, divided by number of times. Even for those zeros, you will have to still count it. You can't omit those zeros saying that he doesn't score, and you will get that 37 example average. Still, if you calculate these deviations, mean deviation, variance, and standard deviation, you will get an understanding. I mean, all these indicators are using each and every individual data points of that batsman's scores to calculate these dispersion indicators. And let's say randomly for these dispersion indicators, I have the mean as 37, and for these dispersion indicators, I get something like, let's say, 20 or 25. What does that mean? Mean as in not the mean. What do you understand by that 20 or 25? That shows you, okay, this guy is scoring on average 37. But a randomly selected value could be as low as 37 minus 25 or 37 plus 25. That's the whole idea. Randomly selected, maybe his next cricket match, how much he will be going to score. It could be, one could say he's scoring an average of 37, so he'll have something similar to 35 or 36, but that will not be the case. His next score could be 37 minus 25 or 37 plus 25 on average, somewhere in between that. I'm broadly highlighting here, not anything defining on the mean deviation or standard deviation or anything like that. But that's the whole idea of dispersion. You need to, let's say, instead of this 25, what if I get, for these dispersion indicators, what if I get a value like 2 or 2.5 or 3? What does this shows? That means, oh, I told you how that 37 is being calculated by zeros and hundreds and 70s. But what if instead of this guy, what if I have the second guy? He has the same average, 37. But every cricket match, he has scored 30s, 32, 35, 37, 39, 42, 43, you know, maybe one or two zeros, maybe one or two hundreds. But mostly his scoring is around 30s and 40s. And his average is also 37 or 38. Okay. When you calculate these dispersion indicators for that guy, you will get a very low number, 2, 2.5. So that means when he comes to the batting pitch, you will comfortably say, okay, his average is 37 and his dispersion indicators like maybe standard deviation or variance is around 2 or 3. So that means there's a very high probability that he will go and bat another 30 or a 40 in this cricket match. That's the use of this indicator that we are going to learn under dispersion. But it's a jolly good example to discuss. But what about some serious examples like sales revenue, a company's profit levels, or biotechnology research? That doesn't really get involved in entertainment, but still the idea of definition is same. Dispersion is all about, we need to understand how scattered this given data set is all about, or sometimes it could be used to get an understanding on the next data point that is going to add to the basket by looking at the historical numbers. Interesting things like stock returns. These dispersion indicators are very highly used in different context and different numbers. You have indicators like beta computation. You can compute a particular stock price with the all share price index and say whether this stock movement is going to be in line with the all share price index or not. So likewise, all these are dispersion indicators we are going to learn one by one. But the whole idea again, what we need is to get an understanding on how scattered this data set are from one another and what will be the next value that is going to be for this data set. Okay. Now these are the dispersion indicators we are going to discuss one by one. Range, mean deviation, variance, and standard deviation. Okay. But again, range is a very simple indicator which will easily give you how much the smallest value and the largest value of a particular data set. But mean deviation, variance, and standard deviation are complex calculations which will give you an understanding with a one particular number to show you from a central point, from a selected central point, how varying your data are. Let's go through one by one and see what these things are. Range, I don't want to even use board here, is a difference in value between the smallest and the largest items in a given data set. Let's say in that example we discussed since the beginning of the afternoon, 7, 3 nines and 1, 10 and 11, 7, 9, 9, 9, 10 and 11. The range will be 11 minus 7, range is 4. What do you mean by the range is 4? Data is ranging from 7 to 11. What about instead of 11, what if we have the 1111? In that instance, your range will be 1104. Why? 1111 minus 7, and the range is extremely high. That of course give you some advantages and disadvantages of the range. It's easy to compute, a simple measure. Ability to get a brief idea on dispersion quickly. You don't have to do a detailed Excel based or a calculator oriented computation. Quickly look at the smallest number, look at the largest number, and get an understanding. Okay, this is the range of items that is in my basket. But you in real life, what do you really use range for? Let's say you go to buy a bicycle, go to a shop, and you have, let's say, 10, 12 different models of bicycles, and you have absolutely no idea on these prices. You will ask the Kade Mudalali, can you tell me what's the range of these bicycles? Mudalali will tell you, okay, Mahatya, I have bicycles in starting from 12,500 to 1,75,000. That's the range. That's the range. 175,000 on one end and 12,500. Quickly you can plot in your mind. Fine. I'm looking for a bicycle for a value maybe 30,000, and you are not very comfortable to tell that number to Mudalali because he will obviously try to sell you a cheaper one because you may not know the real price. Let's say you don't have the price label implanted in, like a lot of Sri Lankan examples. That's why you go and ask for the range. What's the range of prices of these particular bicycles between 12,500 to 175,000. Quickly, easily, you can get an understanding on the dispersion of the range of items. Okay. What are the disadvantages? Not being a representative measure. Likewise, in the mean, MEN, likewise the mean, it doesn't represent any values of the particular data set. But for my bicycle example, what if we calculate the range? I have 175,000 minus 12,500. I may get 162,500, a value like that, which is absolutely not giving me any valuable information. That's just a computed number. Right. It only, last point, it only considers two end values of a data set, nothing in between. It looks at the smallest number and the largest number, nothing in between. That's about the range. You don't have to discuss much on the range. But these are the starting points of our next ample discussions on detailed statistical equations. We are starting from the mean deviation. Okay, we'll take a moment and understand what these are. Average value of absolute deviations from the mean to each observation in the data set is known as mean deviation. Okay, we'll try to use the board and try to get an understanding as to, before we go to these numbers and symbols and try to understand what these are, we'll try to get a classic example and calculate some mean deviation. Let's say I have a set of numbers of 1, 2, 5, 10, 12, Yeah, this is enough. I have 5 numbers. Okay, these are the values. Then the first step that I can do is I can go and simply calculate the mean. I can take the calculator. 1 plus 2 plus 5 plus 10 plus 12 is 30. I have 1, 2, 3, 4, 5 items. I divide it by 6, sorry, 5, and I get an answer. This is x, so individual items, and I get x bar as 6. This is my average or mean. So, what you mean by the mean deviation is simply nothing but how distance each of these numbers are from this particular value, this particular 6. What I can do is I can plot x bar here, 6, 6, 6, 6, 6. I just put this column just for you to easily understand. And then I can write x minus x bar. This column is going to be x minus x bar. This value minus x bar. Going to be negative 5 here, negative 4 here, negative 1 here, positive 4 here, and positive 6 here. So it is clear. This is the first step on understanding what the deviation is all about. You have set of individual numbers, forget about this column. This just I put for you to easily refer and understanding. You have a set of numbers. And then for those set of values, you can calculate the mean. So from mean, how deviated each number is going to be. This is simply but calculated. So, okay. And then statistics, similar to this wording on sigma. There's another definition I'm bringing in. It's a modulus value. Mapanke in single. So the moment you put a particular something here and put these signs of two straight lines here, what is meant by this is you have to take the number only without the sign of it. Let's say for this 4, it will be taken as 4. 6 is it will be taken as 6. But what about this negative 1? Instead of negative 1, I have to take it as just 1. The value is just 1. Instead of negative 4, I have to take it as 4. Instead of negative 5, I have to take it as 5. Just the number, the numerical value. Since we are discussing our discussion on the deviation, what will happen is, students, now if we take these positive numbers and negative numbers of a particular, now this is where the mean is going to be in our data set 1, 2, 5, 10, and 12. The mean is going to be somewhere over here. So the moment if we are going to use the equations on mean variation, if we have these negative numbers and positive numbers, there's a very high chance that these will be crossing off. Just look at these numbers. 4 and 6, the total is 10. What about this number? Negative 5, negative 4, negative 1, this total is negative 10. So if I add in this particular form, I will have nothing but 0. But can this 0 is going to give you some value in here? It's not. What are we going to calculate? For a given number, on average, how deviating it from this value of 6. What is this 6? It's nothing but our average. That's why, so instead of we are taking these negative numbers, we have to take the modulus, the value only, and do these computations. Okay. Let's go back to our slides and see what the definitions are and how we can calculate. Right. Forget about this group data for a moment. Group data we discussed at the second lecture. Once again, I'll iterate. Every time when there's an equation for grouped and ungrouped, I will be defining two equations for you to be comfortable. And each of these instances, if you look at the only difference that you will see in these equations are, instead of this simple n, you will have the simple f, which will denote the frequency of a particular group item. That means instead of taking individual items, you have multiple numbers. Let's say 5 number of tens, 7 number of 11s, 2 number of 20s. So this number of are these simple f that I'm going to discuss in such kind of group data. So the grouping or ungrouping is purely up to the mathematician or statistician to represent. But in pure language, learning an equation for the ungrouped data is the easiest or the much more meaningful thing to do. Grouping is all about nothing but clustering the similar items into a similar group. It could be a class or it could be simply number of items being represented. Okay. Just forgetting the second equation for a moment, we'll focus on the first equation and try to understand how it is being derived. Okay. So the mean deviation is going to be nothing but, we take this, now we are familiar with the sigma, we know what simple I and we know this simple ends and all. We take these individual items, okay, take the modulus value or only the absolute value between the individual values, uh, whatever the number, versus the average number or the mean number which is shown in x bar. Those deviations you divide by this number of items is going to give you the mean deviation, or how deviated you are from the mean. It's a simple definition, isn't that so? I mean, from the equation point of view, it looks a bit you know uh, not very comfortable, but still, if you look at the definition, what do we do here? We take individual value minus the average value, then you have a number. You add all those numbers together, divide by the number of items in the data set, which will give you easily the mean deviation. We'll go back to our board example and see how you can calculate it. Okay. Right. I hope the board is still visible to everybody. My lighting condition is getting darker. It's okay, right?
Yes.
Thank you. Okay. Now we have the, in this column, I have the x in the first instance. Now this is our original data set. Huh? Don't get confused with these other jargon of numbers. This is all what we have. I have 1, 2, 5, 10, and 12. Then I have the mean here. I took those mean to the second column for you to easily, denote the x minus x bar. And then I have these negative numbers. I'm moving from this x minus x bar to x minus x bar modulus, or the value only. So that's why instead of these negative numbers, now I'm going to take the value only. And students, now this is the sigma point. This is the sigma point. These are the numbers that I'm going to add now. I have 9 here, 10 and 20 is going to be the sigma. Okay. You can denote like this also. If you put a sigma and say 20, that gives you an understanding, okay, this guy has added it. We just write total, that's what. Are we done here? No. What are we going to calculate is, now these are the mean deviations. This 5 is 1 deviating 5 number of items from the value of 6. That's the idea. Now these are the totals of these deviations. Last step is, we can divide this number by number of items. 1, 2, 3, 4 and 5. 5 items. 20 divided by 5 is going to give me my final answer for our mean deviation as 4. What does this 4 says? It says for a given number on average, for a given number on average, it is deviating around 4 from the mean of 6. That's the whole idea. This 4, my final answer, I reiterate, is going to tell you for a given selected number, it is going to be 4 value away from my average number of 6. The cricketer score example is the classic example for you to remember this discussion on the mean deviation. You have a mean, still you don't know whether the next number or the he will score a similar value. So you calculate the mean deviation for the previous numbers and then don't get carried away by the mean only. Rather, you get an understanding as to whether he will score a nearby number to the mean or much away. Could be in the next match he may score maybe 100 or 150. You can't really predict, but an indicator shows you that okay, for a particular cricketer, whether the mean deviation is high or low is going to give you some strong sentiment. So in general sense, what do you think? You like a do you like to see much more deviating value or a lesser deviating value? What do you think? I would say I as I'm not a pretty much risk seeker. I like calculated risk. That's my risk appetite actually. So I would say I like a lesser mean deviation. Why? Because my randomly selected value or the next value that is going to come into my basket, I can predict that now. But if I have a cricketer with a average of 37 and a mean deviation of maybe 20 or 30, that shows me okay he can go out with a 0 next time, or he can score maybe extreme values. So both sides are there. Okay. So similarly, the mean deviation is a starting point on the dispersion where the statisticians and mathematicians can easily identify for a particular data point whether how away that is going to be from the average. Right. One quick question. We are discussing about this mean deviation. Mean deviation. I mean, can somebody argue, so why don't you take it as a mode deviation or the median deviation? You could do the exact same exercise, no harm. So instead of x bar, you have the values. But let's try to logically discuss and see if we have the mode here. Okay, instead of the mean, we are going to take the difference of individual value with the mode. Mode is the most frequently occurring number. It may not give you much sensible idea because it's not a good representative. What about median? Median, it could be somewhat useful. It's from middle point. So the middle number, how deviating it are. For the students, we have to bear in mind that the mean and median for a nicely spread out data set, we call it a normal distribution, are going to be perfectly coming to one central point. We call it in the normal distribution session, we are extensively discussing this theoretical part. For a nicely spread out normal distribution, the mean, median and mode, even the mode, all three values are going to be almost coming to the same point, or with a very marginal difference, it is going to come to one central point. So that's why we discuss about the mean deviation and not the mode deviation or median deviation. Okay, we assume that fine for a quite a dispersed data set of maybe hundreds of thousands of data, mean is the best representative, and that's why mean deviation and the next areas on variance and standard deviation, we always take the difference from the mean and not anything else. Okay, right. Let's move on. If you ask me, mean deviation, could we see much more examination questions? I would say not much, but on the next couple of discussions on the standard deviation and the variance. Okay, we'll come to there once we discuss on the advantages and disadvantages of the mean deviation. Few advantages. Good representative measure since all observations are taken into an account. Similarly, the calculation of mean, the mean deviation also, we take each and every value. Re-establish the mean since deviation from mean to each data point is evaluated separately. What do you mean by the re-establishing the mean? That means in our cricketers example, it's a good classic example. We have the mean of 37, and if you have this mean deviation for this cricketer as 2 or 3, that gives you some re-establishment. Okay, the average value, it's not going to be exactly 37 at the next time, isn't that so? He won't score 37, 37, 37 in all the matches. So it's going to be maybe somewhere around 37 or maybe 35 to 39. Likewise, for the next computation of mean with the next number, it's going to give you some re-establishment. And if it is a very large deviation, we can say, fine, this mean is pointless. Maybe you have only 3 numbers. For the first match, he scored 0. Second match, he scored 37. And the third match, he scored 100 or something. Then the average is coming to somewhere around 30s or 40s. And the mean deviation is going to be significantly high number, maybe 35 or 40 in that example. In such instances, if you look at mean, okay, fine, 37. And the mean deviation is 30. Oh my God, you can say, fine, pointless. I don't know whether this mean deviation or this mean is going to be a good number, right? Disadvantages. Not a good algebraic measure since only absolute values of deviations are considered. We'll see this disadvantage and the answer to this disadvantage in the next point on the variance and standard deviation. Just bear in mind that why it is not a good algebraic measure since only absolute values of deviations are being considered and not the deviating from the negativity or the positivity, but all these deviations, the numerical value is only being taken into consideration at the mean deviation computation. Okay. With that discussion, we are moving to the last part of the today's discussion. That is the most important and interesting part of the today's lecture. That is the variance and standard deviation. Now, students, these are the building blocks of the next couple of important statistical lessons. We have to thoroughly understand these definitions, the markings, and there are some few minor definition between the population and sample, how to take the number of items. Those thoroughly you have to understand and keep in mind. Bear in mind, we'll see what variance and standard deviation is. Variance is derived by calculating the average values of the squares of mean deviations. Now, instead of this taking of these absolute values, in variance, we are invited to take the square of the deviation. So instead of this some negative 4, we have to take the square of negative 4. And in childhood, we have learned any number, if you take the square, you will always end up with a positive number. If you take positive 2, take the square of positive 2, the value will be 4. But if you take negative 2, you square it, you will also end up with a positive 2. Okay. So variance is being calculated by just taking the squaring of these items. And the standard deviation is nothing. Now remember, when you take the variance, the deviations are being taken to next level. What is meant by the next level is that when you take the mean deviation, our previous discussion, all these numbers, negative 3, negative 1, positive 5, those are in the same scale of our number range. Okay. But when we take those numbers to the square, to the next level, variance is going to give you, okay, fine, dispersion measure, but at a different level. not at the same level of the numbers that we had in our original data set. So standard deviation is nothing but the taking the square root of this number that we calculated by the variance. So the next slide will have some equations, but bear in mind that you only have one equation, that's for the variance. For that equation, when you take the square root, that's the standard deviation. So variance and standard deviation are not two things, but the same. Only difference is variance, you take the deviations to the next level, but standard deviation, you take the square root again, and then that level of variations that we discuss under the variance will come to the same ground of our original data set. But why we have these two separate indicators, that's a very lengthy statistical discussion, which we'll not have ideally now. But just bear in mind that both variance and standard deviation are being used at different instances in statistics. Okay. Important definitions here. Variance will be defined with a square. Square is this small number 2 here. So variance of a sample will be denoted by S square, while standard deviation is denoted by S. What's this? What's this S? S is the statistical symbol that has been denoted in many statistical books and jargon. You look at the definition. So if you ask for a simple form of an algebraic equation, a lot of us will say y equals mx plus c. So y, m, x, and c, those are the definitions given by the original defining instances. So similarly, this S is coming from this jargon in the statistics. Yeah, for variance we use the S square, while the standard deviation is being denoted by S. The population. Now, this point sample is for the smaller data set, but the population, don't forget that it's the complete data set. This is the symbol, we call it as a rho square and rho for the standard deviation when it comes to the population. But bear in mind, in a lot of instances, in examination questions and many cases, most places we will discuss about this S sample. Why? It's the practical application end of the day. We will not have the luxury to get the variance of the population and standard deviation of the population and all the time. Okay. So bear in mind that capital S square and this rho and rho square are the definitions for the variance and standard deviation for the population and the sample. Now this is how we are going to define those equations. But bear in mind that before we move to this point, let me quickly take you back to the mean deviation equation. Just try to keep this form in your mind for a little while. You have the sigma here, I equals 1 to simple n. Then you have the I minus x bar and some operation. Just forget about the operation. You have the xi minus x bar and then divide by n. Same thing is here. Carefully look at, forget about these rows and s's and all. For the top part, you have the same thing, but instead of this modulus value, now here you have the square individual differences. So xi minus x bar, so this -1, -4, -6 in our -5, -4 and -1 in our class example. Those values you have to take the square and divide by number 5 if it is for the population. So similarly, for the group data and ungroup data, I have two definitions. If you have individual items, ungroup data, you divide by number of items. But if you have the grouping, you have, instead of taking the n, you take by the frequency and the total frequency here. Just bear in mind that this form for the group data is enough for you to keep the equation in mind and apply even if you have a grouping in place. Okay. So for the variance is been defined here for the population, and standard deviation is defined here for the population. Okay, so why I have put this red box here, I reiterated at the beginning. Now this is an equation which you will have to bear in mind. Okay. But if you watch carefully, now this again I reiterate, this is for the grouping and ungrouping. I have just put the simple n and simple f here just for you to get an understanding on the grouping and ungrouping later. I'm moving to the sample, I'm moving to the variance and standard deviation of the population and sample. This light blue color gives you an indication. Okay, this section is for the population, this section is for the sample. But here, if you carefully look at this equation, I have done one small change. Not I have done, but it's the way that it's been defined. For the population, it's fine. The same equation. You take the variance rho square as the xi minus x bar. You take the square value of it, divide by the number of items. Fine. You take this, the square root of this entire business. That's the standard deviation. It's for the population. We are happy. No problem. But for the sample, students, if you carefully look at it, you may say, okay, for the population, you had capital N, and for the sample, we have to take simple n. But instead of simple n, I have taken simple n minus 1. That's the only difference that you have to remember. Now, if I reiterate from this point to the back to the original discussion on the mean deviation, still you will see we are playing with the same equation. You have the x value minus the average value. Either you take the modulus value or either you take the square, and then once you take the square, either you take the entire business or take the square root. That's all about it. Not a big difference up until this point. For the standard deviation and the variance of the sample, instead of capital N, instead of the 700, if our sample size is 50, for the bottom part, we have to take 50 minus 1 as 49, not as 50. There is a lengthy theoretical discussion, which we can have this discussion on different angles. There is one explanation for this coming from a theoretical area called degree of freedom. One coming from pure, simple explanation as to if it is a population, okay, fine, 700 will give you a better number. But when the sample is a smaller one, if your this value is a larger number, you will have a lesser value for the standard deviation variance, which can be a wrong value. But of course, this n and n minus 1 is nothing testable at the examination, and in the interest of time, we cannot unfortunately go to a lengthy discussion. But I implore, if you're really interested, there are plenty of discussion on why it is not simple n, rather n minus 1. Okay. Bear in mind, it's the only difference for a variance and standard deviation calculation in a sample versus the population. Okay. The examination questions also, provided we are discussing about a sample, you have to be very careful and apply the sample size as, if you have the sample as 40 or 30, always take minus 1 for the equation in variance and standard deviation. Red square mean this equation has to go to your A4 sheet in your short notes. Okay, right. I'll give you this as a homework before we start the next class. I'll discuss on this slide and slide number 19. Calculate the sample variance and sample standard deviation. Okay, sample. I have given this as the sample data set, not the population. Use your calculators, calculate and get the answer before the beginning of the next class, and we'll discuss whether we all are in the same page. Right. Give me a second. Just see. Okay, I think we have time to discuss the coefficient of variation also and wind up for the day. But then I think we have plenty of examination questions to be discussed. So in the interest of time, don't worry. What I'll be doing is we'll discuss the some qualities of variance and standard deviation. And then we'll learn the last part of the day on the coefficient of variation. We'll finish off for the day. And then there are some examination questions I have put up here from this slide to maybe 20 more slides. We'll take these examination questions next day when we discuss about the last part also. Okay. Right. And in the meantime, I'll show you what you can complete for the next class, so we can discuss at the beginning if you have any different answers to the correct answer. Okay. Right. Sorry, I think I took a little more time for this explanation, but I think it's pretty important because I can assume that we all are not from the same background, a lot of us. So these smaller things like sigmas and modulus values, these squares and square roots, still it may be a bit more refreshing your ordinary level knowledge. So we have to spend time. We have to get everybody to the same standard. So don't worry. Right. Variance and standard deviation, these are the theoretical aspects. First point, since all data are used in deriving variance and standard deviations, they are good representative measures. So keep in mind that if all data points are being used at any instance, like the definition of mean deviation, mean, variance, standard deviation, those are good measures in statistics. Not like more than. Second point, extent to each observation derived from mean is taken into account. Fine, we understand that. Taking square of a real deviation, unlike absolute deviation, to avoid the mean deviation being zero. This means mathematically accurate. So what do you mean by the mean deviation? If we do not take the, if we really take the correct values for the mean deviations, like these -5s and -4s and -1s, we will have the value of zero. That's why for the mean deviation, instead of the true value, we take the crafted value. You take a crafted new value or a artificial value. But in the variance and standard deviation, we don't do that. We take the square. So automatically, these negatives and unwanted numbers has become positives and help us to come to this new equations. Deviations are over-evaluated in variance, but standard deviation takes out the weakness. This is the weakness that I told you, that we are moving this number set, this deviation number set, to a next level. Over-evaluated. But standard deviation, the moment when we take the square root, that's the answer to that weakness. Last point. Standard deviation is the best measure of absolute deviation to compare different distributions with same unit or similar means. What do you mean by that? Is that it's the best measure if two data sets has a similar mean, similar average, two batsmen, 37, 37. Same units, 37 cricket marks, 37 cricket marks, same units. And then if you have two standard deviations, first guy has a standard deviation of 20 and the second guy has a standard deviation of 2. We can say we prefer the second gentleman or the lady cricketer, because for that person we can predict the next value with much more accuracy. That doesn't say that he will always end up with 37s, but pretty much the deviation, the lesser the deviation, mathematicians, statisticians, financial experts likes the numbers. That's about the qualitative aspects on the variance and standard deviation. Don't worry, we have plenty of exam questions to discuss. Last theoretical point we want to touch upon is the answer to this same unit problem. If we have same unit, same cricket marks, fine. But in real world, we have different units and different averages. You know, that cricket guy's example of 37 marks, fine, it's pretty much understood. Both guys are having 37 marks. But if the first cricketer has an average of 50 and the second cricketer has an average of X bar as 37, then still that comparison is not like with like, isn't that so? We are comparing 37, okay, with some sort of a dispersion indicator of 2. 37 minus 2 or plus 2, okay, we can get some understanding. For the second guy, 37 with a dispersion indicator of 20. Okay, it could be 37 minus 20 plus 20 to different degrees. We are clueless. So the same discussion we can't do if we have two X bars. Instead of 37s, we will have 137 and 150. One average of 37 and one average of 50. Now we are helpless. That's one instance. And the second instance is when we have two different units. That's also a problem. That is the last answer on these measures of dispersion we are going to discuss as coefficient of variation. It's a very simple definition. It's just a ratio. Carefully look at it. It takes the standard deviation value divided by x bar, or the mean, the average. So mathematically, if you really look at this number, what we get is for 1 unit of x bars, 1 unit of average numbers, how much standard deviation are there? Let's say 37 is the average for the first guy with a standard deviation of 2. Okay. Now 2 divided by 37 is the first gentleman's coefficient of variation. For the second gentleman, coefficient of variation is going to be 20 divided by 50. Now, students, we have converted those means and standard deviation into one comparison ground. And now we can compare those two cricketers and say, fine, which cricketer with less deviation we are going to like now. Like now. That's the idea of the coefficient of variation. Though using these measures of absolute dispersion as in these are absolute indicators, absolute numbers. The dispersion number is going to come from the same unit of numbers we are going to discuss. This is a relative measure. Why? We take a ratio, relative, a percentage, as absolute dispersion to compare variations in distribution. Data sets with different units and significantly different means shall derive wrong conclusions. If you do a comparison, we derive a wrong conclusion. So measures of relative dispersion percentage can be used to compare such distributions, and coefficient of variation can be used in such instances. So once again, I tried. If it is in a red box, it's the equation that you have to keep in mind. Okay. There are plenty of 2-mark examination questions just asking you to compute this coefficient of variation and make a decision whether you like more variation or less deviation. Is up to the examiner's questions to form it in that way. But bear in mind, coefficient of variation is not a detailed equation. It's just taking the ratio of standard deviation to the mean. Okay, that's it. And now this is also an important thing to show you. I mean, you may have learned this, but over time you may have forgotten. If you multiply this any number but by 100, and if you use a percentage mark, what does this indicate? This percentage mark in mathematics will be denoted as 1 divided by 100. So 100 multiplied by 1 divided by 100 is going to give you this value as 1. That's why whenever there's a percentage being involved, carefully write it as not being multiplied by 100 but 100%. You can't merely multiply anything by 100 and say it's a percentage, but rather this is the correct way to define. Okay? Small things. Right. This I will again view as a homework, slide number 22. Before the beginning of next class, we are going to discuss this. I want you to calculate the coefficient of variation for the below two data set and interpret the results. You have these data sets. Set X has 1, 2, 3. First, you have to calculate the X bar and then calculate the standard deviation. Then you can calculate the coefficient of variation by dividing the standard deviation by the mean. You have two data sets, 1, 2, 3, 100, 200, sorry, 101, 102, 103. And then I want to interpret the result. I want for you to give me a bit of a write-up. Okay. as in I want to interpret whether compared to X, what do you see in Y? Compared to Y, what do you see in X? That's the whole idea. Fuel prices in two countries, country A and country B. I have some fuel prices of this particular country in one unit, this particular country in another units. So again, I want you to, these data sets will be, two data sets is given to give you an understanding of two particular instances of the usages of coefficient of variation. So calculate it, come up with the answers in the next day. We can discuss it at the beginning of the next lecture. I am going to stop at here for the day. I'll call it a day now. We have examination questions from slide number 23 until slide number 38. But I want you, don't worry, each and I mean, there are some questions, those are seems to be like duplication. So same examination question. If it's an interesting question, or students, if they have find it a bit difficult, say there's a big probability for the examiner to test it again and see whether students has understood it now correctly. So except those questions, we will go through each and every of these questions one by one. But what I want you have a week's time. Take your time, try all these questions on your own, and before the beginning of the next theoretical lesson, which will start from part 2, we'll spend some good half an hour to 40 minutes and spend our time to see whether we all are getting the same answers or whether your answers are slightly different. That's for the day, and we will be starting from part 2 once we discuss the last week's questions, and we will discuss these theoretical areas on skewness, kurtosis, covariability, and go into the end of the section 3 on next week, hopefully. That's it for the day, and I'll stay in the chat for a little while. If you have anything to be discussed, you can raise it, otherwise you are free to go.
Thank you, sir.
Welcome. Yeah, I think yes, about the background noise, I'll work on that. Yes, thank you for that point. I at one class I tried to just use these microphones with a headphone. I think that helped me a little, but I think the bird noises and all is going to be a bit distant. Yes, thank you for the point. I'll try to make an amendment by next week. Okay, ladies and gentlemen, then I'll call it a day. But even if you have anything to be discussed, just shoot it in the IBSL mail. I'll come back to you on that. Okay then. Cheers. Have a good evening. Bye bye.